The Z transform is a more general transform than the Fourier transform, and it's widely used in discrete time signals and systems, and we're going to use it in filter banks and wavelets. And now we'll look at the effects of sampling and some more tools in the Z domain. Since we usually deal with causal systems in practice, we're going to use the one-sided Z transform as defined by this summation here. So it's going from the causal system, is going from 0 to infinity. This is the signal in the discrete domain, the samples n, and this is z to the power of minus n. So observe that this simply takes our sequence x of n and turns it into the polynomial x of c. So this is very interesting from the Z transform, that it turns a sequence into a polynomial, and we have many tools that we can use with polynomials. So first observe that we get our usual frequency response, the DTFT, the discrete time Fourier transform for a causal system signal. So n is starting at 0. If we evaluate the Z transform along the unit circle in the Z domain, so when Z is equal to the e to the power of j capital omega, we are evaluating the Z transform along the unit circle in the Z domain. And this here connects the Z transform with the DTFT, the discrete time Fourier transform, except for the sample index n, which for the so-called one-side Z transform starts at n equals to 0, and for the DTFT starts at n equals to minus infinity. In general, we can write complex variable z with an angle and a magnitude. So here we can interpret the capital omega as the normalized angular frequency, and the r is a damping factor for an exponentially decaying oscillation if r is smaller than 1, or exponentially growing if r is greater than 1. So observe that this damping factor is not in the DTFT. This means that the Z transform, in the Z transform we can have a converging sum of the transform even for unstable signals or systems, just by choosing r large enough. This means that the region of convergence, the ROC, just becomes smaller. Remember, in the Z transform sum we have z to the power of minus 1 is equal to 1 over r times e to the power of minus j omega. So the recommended reading for this part is the discrete time signal processing by Oppenheim, and we can also see there's an MIT Open courseware. This is the class offered by Professor Alan Oppenheim, discrete time signal processing, and we find here many interesting things like lecture notes on different topics. So we have minimum phase, all pass systems, group delay, quantization, FIR and IIR filter structures, filter design, multi-rate systems, revisions, DT, the discrete Fourier transform, FFT algorithms. So it's a very interesting course. So I recommend to take a look at the book, The Discrete Time Signal Processing, and the MIT Open courseware for the Alan Oppenheim course, Discrete Time Signal Processing.